Okay, so in this movie clip, let's begin with a BJT with a narrow base. Okay, so most likely in modern BJT device structure, the thickness of base is super thin. So narrow base is a widely adopted device design guideline. So why narrow base is necessary in designing the BJT device structure? So for that purpose, you may uh, well, why we are learning this a very advanced one? Well, this very thin narrow base is a required one in designing BJT device. Okay, so let's start here. So in practice, again, so in real BJT device, we should make the the width of quasi-neutral base region, not W sub B, physical thickness. I'm talking about the W. Well, usually W is smaller than WB because this W does not include the depletion layer for from emitter base junction as well as collector base junction. Okay, so we should make W much shorter than the L sub B. So this L sub B indicates in the case of PNP BJT, the base is n-type. So here S sub B means a minority carrier in the n-type should be whole. So whole diffusion length. Okay. So we make W smaller than shorter than L sub B. What is the main purpose of it? Yeah, the answer can be found here. We would like to implement and achieve very high current gain. Okay, so for that purpose, narrow base is necessary. Okay, why narrow base? High current gain it should be the main goal. So for that purpose, I mean, to do the quantitative analysis, why the narrow base is necessary for the BJT device, let's go back to the complicated equation again. So hypersine, hypercosine. So in the previous slide here, uh, let me erase it. You may see the many hypersine and hypercosine here and there, right? So if the terms for hypersine, the terms for hypersine is very smaller than 1, then hypersine x, I mean, instead of cosine, I prefer to use x. Anyhow, let's follow the lecture note. Hypersine cosine is asymptotically approaching to the cosine. Okay, so I mean the hypersine x is equal to x when if x is much smaller than 1. And hypercosine is this, okay, when the cosine is much smaller than 1. Okay, so remember those two terms. Why we got this? Please go back to your calculus textbook. Okay, and then you can see that the full derivation for that. Anyhow, let's go back to the excess hole concentration in the base as a function of x. In the previous slide here, yes, there we go. Here, delta P sub B has been written with this equation, but if this, this whole value and that whole value is much smaller than 1, then you can simply take it out, take the hypersine symbol out, okay, and same as here. But to do that, this value should be smaller than 1 and this value should be smaller than 1. For that purpose, take a look at here. W over LB much smaller than 1. That means W is much shorter than L sub B. Okay, so if narrow base has been well made in your BJT, then you can simply take out the hypersine symbol. Okay, all right, then let's go back to here. Then let me see. So now hypersine has gone. And now take a look at here. L sub B is common, so you can cancel out. and the W is here and W minus X. So if I write down it here, W minus X over W is 1 over X over W. Okay, so please remember this guy. So instead of this complicated hyper sign, just ignore it and plug in the 1 minus X over W. Okay, so this guy times 1 minus X over W. Remember it and let's move forward. There we go. This guy times 1 minus X over W. Okay, when if this W is much shorter than L sub B. If this condition has been well satisfied, then the complicated equation for delta P sub B can become very simple. Okay, let's move on to the second term here. We have removed the hyper sign and take a look at this and that. And LB is common, so cancel out and X over W. X over W. So this whole term, PB naught exponential V sub CB collector base junction, blah blah blah. This looks like a diode equation, right? Times X over W. Yeah. This guy times X over W. Okay. So this equation for delta P sub B as a function of X is a kind of simplified version when the W is much shorter than L sub B. The full version of the equation for delta P sub B as a function of X is given here. Okay, that is a full version. But if, as long as the quasi-neutral base region total width is much shorter than L sub B minority carrier diffusion length, then you can use this simplified version. Take a look at here as a function of X, X and X. This is kind of a y is equal to ax plus b, first order polynomial equation. Very simple one. On the right hand side now, where is my pen? Okay. On the right hand side, you can see the base region from x of 0, x of w, and the y-axis indicates delta p sub b as a function of x. So when x of 0, when x of w, this point and that point has been well written previously in the right previous movie clip. I have written down this value and that value, right? So please go back there if you're interested. All right, so in the previous slide we have done how to simplify the excess hole concentration in base region, and now it's time for us to develop the full equation for 4 different BJT performance parameters. Gamma, what was it? Gamma is emitter efficiency. And what is alpha sub t? Base transport factor. What is alpha sub dc? Common base dc gain. What was beta dc? Common emitter dc gain. Okay, so those 4 major performance parameters has been well defined in the previous lecture note. If you have missed it, please review those 4 the definition of those 4 BJT performance parameters. But in herein why I have got those 4 performance parameters back onto our discussion table, we would like to fully develop the full equation for those 4 performance parameters. I mean, once you know the doping concentration in emitter, base, collector, and once you know the intrinsic carrier concentration in your base region, collector region, emitter region, well, what if you are using the non-silicon material for base region only? Well, actually, that was named as a heterogeneous Bjt, so HBT stuff. Okay, so if you type in the HBT in searching box, maybe Google searching box or others, then you can see that heterogeneous Bjt has been widely adopted in an analog integrated circuitry. So N sub I, the intrinsic carrier concentration in base, intrinsic concentration in emitter would be different if we are using different material. Then, silicon based PN junction is kind of homogeneous junction. But say that P side is germanium based P type material and N side is silicon based material. Then germanium, silicon, those two different materials are in physical contact. Then we can say that that is a not homogeneous junction but heterogeneous junction. Anyhow, with many material parameters, how to define the BJT performance parameters, gamma, alpha T, alpha DC, beta DC. For that purpose, I have prepared this lecture note. What is the definition of this gamma? Gamma is IEP plus IEN, IEP. So how much emitter current by hole can be well delivered, well emitted out from the emitter, okay? So we would like to increase IE sub P compared against IE sub N, okay? That is the main reason why in PMP design, this emitter base collector, the emitter side should be very heavily doped, okay? Then IEP is a dominant one compared against the IEN. So emitter efficiency, the maximum value of this emitter efficiency would be 1, okay? But usually less than 1 because of this I sub En. Then now it's time, since in the previous lecture note, we developed the full equation for IEP and IEN. Where? Yeah, there we go. IEN and IEP. So gamma is defined as IEP over IEP plus IEN. So plug in this very complicated equation in this, then do your own, some job, and in the end, you're gonna get this work. You're gonna get this equation for gamma. Please do that. Well, this time I don't want to hand out another homework problem set, but just for you as just for your information, please do that. Okay. So emitter efficiency. And now let's move on to the base transport factor. What was the definition of this? Alpha sub t. Yeah, ICP over IEP. Once a hole has been injected from emitter, how many holes are arrived into the collector? That indicates a base transport factor. So ICP, IEP. Where is it? Yeah, ICP, IEP. So using those two complicated equation, plugging into alpha sub t here, this, then you're gonna get this simplification. Take a look at here. If W is much shorter than L sub B, this guy, that would be approaching to 0. So alpha sub t would become 1. That is the thing that we would like to have. So why narrow base is necessary? Well, alpha t would asymptotically approaching to the theoretically maximum value. Okay. All right. What about the common base DC gain, alpha sub DC? And what about the beta DC? Please do that. Go back to the definition for those two performance parameters and plug in, those full parameter current components. Then you're gonna get this complicated equation. So please do that. Have your own time to develop this full equation. And one thing that I want to explain it is here. If W is much shorter than L sub B, narrow base BJT, then this is a second order term, right? So simply this value would be much smaller compared against this value, okay? So in this case, you can ignore the second term. So in the end, you're gonna get this equation: NIE squared DE NBW, and this whole term would moved up, NIB squared DB NE LE. Okay. All right. Okay, that's all. All right. I guess the next upcoming one is Eber-Small model. So Eber-Small model has been widely adopted in explaining how the current is flowing in PNP and NPN BJT device. So the basic idea is very simple. Since we know all the current components, let's sum them up, then we may build up our own circuit model, how the current is flowing across the BJT. Okay, so in this lecture note, you can see that the IC versus VCE or VEC, since we're studying the PNP BJT. Okay, so VEC is here. So emitter collector junction voltage, right? And the collector current. So I'm talking about here. So emitter, collector, base. So emitter, collector, voltage difference, and how much collector current is flowing. Okay. So this counterpart is PMOS. Okay. Source, drain, gate, and source to ISD. Okay. So for given VSD, source to voltage, VSD, how much source to drain current is flowing? You know this, right? In MOSFET, in P-type. Since this is P-type, so if I'm using the real polarity, then usually x-axis is VDS instead of VSD. So the current is formed in this direction. That is a real one. But since source and drains are switched together so that everything, all the measured, the real data has been drawn instead of third plane, the measured data has been drawn in first plane. All right, and yeah, well, let's go back to the Eber-Small model. That is a person's name. Okay, so Eber-Small model, what is it? Eber-Small model is a large signal equivalent circuit. Okay, not small signal equivalent circuit. That is the small signal equivalent circuit should contain the parasitic capacitive components of BJT. But herein, I'd like to explain the large signal equivalent circuit. Okay, so this Eber-Small model has been used to describe both the active region and the saturation region of BJT operation at a time. Okay, again, at a time we can develop a certain kind of equivalent circuit to explain how the current is flowing when the BJT is under active mode, when the BJT is under saturation mode together. So single equivalent circuit can be adopted and used for two different operation modes, active and saturation mode of BJT. Okay, so this model is going to be used to estimate base current I sub B and collector current I sub B for a given base emitter voltage and base collector voltage as described here. Okay, so actually current versus voltage characteristic can be well described with this Eber-Small equivalent circuit. So now let's take a look at how to develop the Eber-Small equivalent circuit. So on the top, you can see that emitter current and collector current. Okay, so how to get this equation? Well, go back to here. Yeah, IE and IC, those two. Okay, those two equations has already been developed. So let's bring them here. Okay, bring them here. All right. So now let's do two different jobs. What if only emitter base voltage difference is applied. I mean the collector base voltage difference is 0. So I mean that this is a PNP BJT, and the voltage difference between collector base, I mean here plus minus collector base voltage difference is 0, but emitter to base voltage difference is non-zero. I mean the only this junction, emitter base junction is, you know, not in thermal equilibrium, but this base collector junction is in thermal equilibrium. Okay. Then let's write down the emitter current again. So how to do that? Just simply plug in zero value here, 0 voltage, because V sub CB is 0. Okay, so if exponential 0, that means total is 1. 1 minus 1 is 0. Something times 0 is 0. So just ignore the second term. Okay, and now this exponential QVEB over KT minus 1 has rewritten here. It looks like a diode equation. And this whole parameter coefficients are combined and rewritten with this single term IF naught. Okay, all right. So here again, IF naught. Take a look at it here. I'm going to explain a reciprocity relationship soon. Okay, and now let's look for the collector current I sub C when VEB is non-zero but VCB is 0. So go back to the equation here. VEB that is non-zero, but VCB is 0. Okay, so then that value is 1. 1 minus 1 is 0. So now you can ignore the second term. Okay, and this part has been rewritten again here, and this part has been written as alpha f times IF naught. How come IF naught has popped up again? Well, take a look at this equation, up and down one. Looks very similar, right? Even this guy and that guy is very similar, right? So alpha f times IF naught. Okay, so let me erase. Okay, so this whole value is defined as alpha f times IF naught, and this whole value is defined as IF naught. Then from this and that, you can guess the alpha f as well. But alpha f times IF naught, there we go, is defined as what? Yes, here, there we go. Okay, so this whole term, QA times, right, dB over LB, you can see that, dB over LB, and PB naught here, PB naught, and hypersign, where is it? Hypersign W minus LB, hypersign W minus LB, okay? And IF naught is defined as this, okay? All right, so now we are done to look for the IE and IC. When VEB is non-zero, but VCB is 0. Okay, the last job herein is, let's look for the base current, IB. How to get it? You know, collector current is emitter current plus, okay. Emitter current is defined as IB plus IC, right? So, as shown in here, that is IB, and that is IC, and emitter current is this, right? So IE is equal to IB plus IC. That is kind of KCL, Kirchhoff current law, right? So since we know the IE and IC, IB is very simple job. So IB is IE minus IC, okay? So this minus that, and since this exponential terms common, right? So IF naught is also common, right? So 1 minus alpha f, those two. Very simple. Okay, so we have done the first job. Now let's move on to the next job here. This time, VCB is non-zero, but VEB is zero. Okay, so I mean the emitter base junction is in thermal equilibrium. However, collector base junction is not in thermal equilibrium. Then how to simplify the current equation, IE and IC? Okay, so let me erase my note. Okay, so plug in zero value into the VEB here. Then this whole term is gone. Then and what about here? Zero. Then all the terms are gone. Then IC here. IC is equal to this guy. Okay, and IE is equal to this guy. Okay, but take a look at this term, exponential QVCB over KT minus 1 and another one. Those two are common, right? So you can clearly see that this and that common terms for IC and IE. And next one is here, minus has been delivered here, and IRO is defined as this. That is IRO. What about here? Alpha R times IRO. So minus is delivered here, and this whole term is defined as alpha R IRO. But take a look at this term, second term, alpha R times IRO. This term. And let me see. Alpha F times, no, something, oh, sorry about that. So IC here, IC is defined as that is gone because VEB is 0. So minus IRO times this exponential, okay? So you can see that here. And IE, this time here, IE is defined as that term has been gone because VEB is 0. So minus and something times exponential stuff. So minus something times exponential stuff. So take a look at here. Minus, no, this is alpha R times IRO. Take a look at this term. And when we define the alpha F times IF naught, we define it as this. So take a look at this term and take a look at this term. So let me erase my note. Take a look at this term and this term. Well, definitely QA should be here. Take a look at it. Same or different? Same, right? So you can see that reciprocity relationship is defined as this. Alpha F IF naught is equal to alpha R IRO. That is QA blah blah blah. Okay, that is quite interesting. Okay, so we have finished to develop the equations for IC and IE. When VEB is 0, but VCB is non-zero. The last job is, let's look for the equation for base current. So base current, again, is defined as IE minus IC by KCL. Then you're going to get this equation. So we all set. And now, please read out this sentence. In general case, VEB, VCB both are non-zero. In the previous slide, we have assumed that either of junction voltage in BJT, I mean here, this or that, VEB or VCB, either of it should be 0. But this is very special case. In general, VEB, VCB are non-zero together. Therefore, when we develop or write down the equation for emitter current, i.e., this term, number 1, and that term IE number 2. So IE should be IE coming from number 1, IE coming from number 2. Okay, simply sum them up. Okay, then you're gonna get this equation, right? Take a look at it again. IF naught exponential stuff minus alpha RI some exponential, and sum them up, right? IF naught exponential minus alpha IRO exponential, right? So similarly, you can do the same job for the collector current. So that is IC when CB is 0, but VEB is non-zero, plus another IC when VEB is 0, but VEB is 0, but VCB is non-zero. Okay, going back to here, this guy number 3 and that guy number 4, please sum them up, number 3 and number 4. Then you're gonna get the equation for collector current in general case. Okay, now take a look at these two equations. This is the emitter terminal node, that is base, that is collector. And now collector current, base current, and emitter current is defined as we have done, IB plus IC. Okay, and IC has been well written here. Two current components, right? Here, take a look at this guy. IR naught times exponential QVCB over KT minus 1. That means, collector to base, right? That is base. So plus minus. Collector to base biasing, the voltage difference between collector and base would be used. How much current is flowing from collector to base in this direction. So these all terms are denoted as IR, and that IR naught times exponential stuff. That is quite similar to the general diode equation. I is equal to I naught times exponential QVA over KT minus 1. How to define it for a given PN junction diode, right? So VA indicates the plus minus voltage difference between P side and N side, and current is flowing from P to N. Take a look at here. Current is now flowing from P to N side, right? This is PNP BJT. So collector to base, the current is flowing, IR, and saturation current I naught has been used. So here I have used the R, so IR naught, right? And the current direction is quite opposite of the collector current direction, since the current is now flowing in the opposite direction of IC. Okay, so this second term can be written with a diode symbol, right? Okay, what about this guy? This guy can be written as here, alpha f times IF. So IF means this whole term, IF naught times exponential stuff, okay? So alpha f times IF is denoted as a current source. So this current source is nothing to do with the voltage difference between base and collector, right? This current, the total current, alpha f times IF, is the function of emitter base voltage difference. Okay, again, this current component is nothing to do with the VBC. However, this current component is controlled by the emitter base voltage difference. Okay, so this two terminal voltage difference is nothing to do with current, the total amount of current flowing. This third voltage, the voltage difference at very different terminals would control the current flow. Okay, so in that sense, as you have learned in the linear circuit analysis, the independent current source would be the right choice to describe and to write down as a circuit symbol in between base and collector. Okay, so diode and current source would be used to write down the collector current. Okay, so similarly, you may build up the another diode and current source between emitter and base side, as shown in here. So this whole guy is defined as IF, and this whole guy is defined as IR. So alpha R IR is defined here as a current source, and this whole IF is uh, written with a diode symbol. Okay, then this black box, right? Emitter, collector, and base. So this black box, you can now understand what kind of circuit components are included in this black box. And that black box is corresponding to the single, you know, no, this way, BEC, okay? This simple BJT circuit symbol can be equivalent to these two diodes and two current source, okay? So that is the core part of the Ibra small model, okay? So in the next upcoming movie clip, I'm going to explain the base width modulation and how to modify and address the base width modulation and the early voltage width array. I guess this part is quite corresponding to the short channel effect in MOSFET. Okay, in MOSFET, as the channel length has been aggressively scaled down, the transistor has become non-ideal. Same event would be happened once base width has been modulated. So we are going to learn it in the next movie clip. Thank you for your attention. Bye bye.